Similar to the aliphatic nucleophilic substitution reactions, the SN type reactions, we have aliphatic electrophilic substitution reactions. And in this video, I'll be discussing with you one of the mechanism, aliphatic electrophilic mechanism, that is SE1 mechanism. Now, aliphatic electrophilic substitution reactions involves the replacement of an atom or a group attached to the aliphatic compound by an electrophile. In a nucleophilic substitution reaction, it is a nucleophile which is the attacking group. Here it is the electrophile which is the attacking group. Now the group which is replaced can be any group on the carbon. It must be a good leaving group which will leave the shared pair of electron on the carbon. So proton also can be the leaving group, or proton can also be replaced by an electrophile. Usually it is difficult. It depends upon the acidity of the proton. If the proton is highly acidic, then the proton on the alkane can also be replaced by an electrophile. So protons like this, the proton adjacent to carbonyl carbon, can be removed easily and can be replaced by an electrophile. And the proton adjacent to the triple bond acetyl proton can also be replaced. So when the proton leaves, what happens? The proton will go off as H plus ion, and negative charge will be present on this carbon. And the electrophile can come and attack this carbon, negatively charged carbon. Now, similar to the CH bond cleavage, we can also have CC bond cleavage, wherein an alkyl group will be the leaving group, CC bond cleavage, and when that happens, we get a carbanion and a carbocation. This carbocation will be the leaving group, the carbanion will be remaining there, and the electrophile will come and attack on the carbanion. So this is also possible. Now, there are 4 types of aliphatic electrophilic substitution reaction. One is the SE1 mechanism, then you have the SE2 front mechanism, and SE2 back mechanism, and SEI mechanism. And these are all analogous to our SN1, SN2, and SNI. SE1 is a unimolecular reaction, while the rest of the 3 are bimolecular. We'll be discussing each type in detail. Now we'll take up the first one, that is the SE1 mechanism. Substitution, electrophilic, unimolecular, which is analogous to SN1 mechanism. Now here, as in the case of SN1 mechanism, this was also follows a 2-step mechanism with carbanion as an intermediate. In SN1, it was the carbocation. Here we have carbanion as the intermediate. Now, if we look at the steps of the reaction, first the substrate cleaves to form the carbanion. Alright, and then to this carbanion, an electrophile will approach and a new bond will be formed to give us the product, substituted product. Now, the incoming electrophile can be H plus, Cl plus, NO2 plus, alkyl plus, etc. Similarly, the leaving group also can be similar compounds, similar groups. Alright, the only thing is the leaving group will leave with a positive charge on it. So, if we can summarize the steps involved in the SE1, we need to generate an electrophile. That is not involved in the rate determining step. Then the formation of carbanion, which is the intermediate, is the rate determining step. And then immediately once the carbanion is formed, the electrophile will add up onto the intermediate and form the product. So this formation of carbanion is a rate determining step. Now, what are the evidences for this proposed mechanism? 2-step mechanism involving only the rate is being determined only by substrate concentration. Now, one evidence is the base catalyzed hydrogen exchange. When the compound is treated with base, hydrogen is deuterated base, the hydrogen is exchanged, and we get deuterated compound, and the rate of deuteration is independent on the concentration of the base. Alright, you take deuterated base or undeterated base, you get this. The exchange is same, independent. The rate is same. That is, here the rate of the reaction is independent on the concentration of BD. Similarly, base catalyzed tautomerization. We have acid catalyzed and base catalyzed, but base catalyzed tautomerization follows SC1 mechanism. Now, this is the steps involved in base catalyzed tautomerization. You can see here this is a ketone. Now, the proton is acidic. It can be easily removed by the base OH minus. So you get carbanion. These are the enolate resonance forms. Okay, and you get enol here. So the ketoenol tautomerization is independent on the concentration of the base. And this shows this when you use deuterated base or you use heavy water, D2O, you get deuterated ketone. Alright, so that means it shows what is called the isotope effect. Okay, this base catalyzed tautomerization exhibit isotope effect, but then the introduction of the isotope is independent on the concentration of the D2O. It is dependent on the concentration of the ketone. Alright, now let us look at the stereochemistry of this mechanism. Now, it is difficult to predict the stereochemistry of mechanism because of the configuration of the carbanion. The carbanion formed can be pyramidal or planar, or sometimes it will acquire a configuration which is in between this pyramidal and planar, in between these two forms. That depends upon the substituents on it. So owing to that, the product we get can be a retained product, an inverted product, or a racemic mixture. Now in SN1 we could say that we usually get a mixture of product. We don't get a retained product completely or an inverted product completely, depending upon the ion pair formation. We get either a racemic mixture or an inverted product or a retained product. Now here it is difficult to predict, and our carbanion will be, if it is pyramidal, acquiring a pyramidal configuration. Usually it acquires so because of the minimum energy of the pyramidal configuration. This is favored. But even when it is in the pyramidal, when it is in the pyramidal configuration, when the carbanion acquires the pyramidal configuration, if it is retaining this configuration, we get a retained product. The leaving group leaves from here, incoming groups comes here. But if this pyramidal configuration gets inverted, what happens? We get the racemic mixture, because this is called pyramidal inversion. That is, this pyramidal configuration gets inverted, so the incoming group will be attacking from the back side. Alright, the configuration changes and we get the racemic mixture. Because of the pyramidal inversion or pyramidal flipping. So such inversion is observed in amines, tertiary amines. So, and we know that carbanions are isoelectronic with tertiary amines. So this pyramidal inversion is observed here also. So if it acquires a pyramidal inversion, if the carbanion holds the pyramid, then we'll get retained product, but if it is flipping, then we get racemic mixture. Okay, and remember, when it flips, it doesn't completely flip. An equilibrium is acquired between the two forms. Now, if it is a planar structure, if the carbanion is a planar structure, then also we get racemic mixture, because this, when the carbanion is formed, the electrophile can attack from either the back side or the front side. So we get a mixture of the inverted and the retained product, and we get a racemic mixture. So usually what is observed is racemization. So when we talk about the stereochemistry of SE1 mechanism, we can say that racemization is a result. We get both inverted and retained product. Now, that is independent upon the oscillating carbanion, pyramidal carbanion, or on the planar carbanion. Usually we get racemic mixture. And what is the reason? Is it because of the planarity of the carbanion, or because of the flipping pyramidal carbanion is not confirmed yet. Now, what are the various factors which decides the rate of SE1 mechanism? We have different factors: the substrate, the nature of the substrate, the nature of the leaving group, and the nature of the solvent. The incoming electrophile is not going to affect the rate of the reaction, because we know it's a unimolecular reaction. Let us take up the effect of substrate on SE1 mechanism. Now we know that the substrate must form a carbanion, and the formed carbanion must be stable. So the substrates with electron withdrawing groups on it will increase the reactivity, because when the carbanion is formed, it will be stabilized by the electron withdrawing substituent by -In effect. The electron withdrawing group will pull the electron charge towards itself, making the carbanion stable. So the reactivity, the order of reactivity, we can say that the methyl substrate is more reactive than ethyl, then propyl. This would be the reactivity, because the carbanion has to be stabilized. Remember, the opposite is the reactivity series for SN1 mechanism, because there a carbocation is formed. And one more thing, we can say that the increase in bulkiness of the substrate will decrease the reactivity. And also presence of electron donating group will decrease the reactivity. So one more thing, SN1 reaction is not possible on the strained bridgehead, but SE1 is possible on this carbanion here. On the bridgehead also it is possible. Alright, so that is the effect of substrate. And now effect of leaving group. Usually if there is a good leaving group, the reaction will be fast. So the Cl bond, polarity of the Cl bond must be is a decisive factor. Highly polar the Cl bond is, more easy will be to cleave the Cl bond. So usually we expect the if the leaving group is a metal, we expect it to leave easily than a CC if it is a CC, a carbon-based leaving group. But SE1 mechanism is more favored where there is CC bond breakage, and the reason for this is still unknown. Usually the reaction which involves CM bond breakage is SE2 mechanism, and which involves a CC bond breakage is SE1 mechanism. Why is that so? Why is this unexpected tendency or an unexpected pattern is still not known? Another factor which can affect the rate of SE1 is the solvent. Now, we know that SE1 reaction involves carbanion intermediate, so a polar solvent will will increase the rate of the reaction. So you increase the polarity of the solvent, the rate of the reaction will increase. That's because you have carbanion formation, and the polar solvent will solvate and stabilize the carbanions. Okay, and also this will decide the stereochemistry of the reaction too. Because if the solvent solvates the carbanion leaving group and the carbanion and the leaving group together, then you get an inverted product. But if the solvent is solvating only the carbanion, then we can get a racemic mixture, both the inverted product, and we'll get both inverted product and retained product. So the solvent decides. You increase the polarity of the solvent, the rate of the reaction increases, and the solvent also decides the stereochemistry of the reaction. Now, coming to the various reactions in which we find SE1 mechanism, we have all these. I've listed few reactions, almost 8 reactions. We shall take up each reaction one by one quickly and see how these reactions proceed via SE1 mechanism. Let us take the first one, that's the decarboxylation of aliphatic acid. Now, aliphatic acids with functional groups like COOH, aromatic ring, NO2 group attached to it, or a double bond or triple bond at alpha beta position, can undergo decarboxylation reaction via SE1 mechanisms. That is, one CO2 will be lost. So the mechanism is like this. You have the carboxylate anion here. Now that will, the electron on the oxygen will go back to the CO bond, and CO2 will be formed, and you get the carbanion here. This is the carbanion intermediate onto which an electrophile can attach. So the CO2 is lost from here. So if you have a dicarboxylic compound, Z will be COOH here. Okay, and if the incoming group is a proton, you get an alkane here as a product. Okay, so the rate of this reaction depends on this carbanion, on the substrate, on the carboxylate anion or the carboxylic acid. When a carbon dioxide is lost from a dicarboxylic acid, malonic acid undergoes this one. We get monocarboxylic acids of higher order. So this is the dicarboxylation of aliphatic acid. Another one is cleavage of alkoxides of tertiary alcohols. Okay, alkoxides of tertiary alcohols, again to which an electron withdrawing substituent is attached. Remember, an electron withdrawing substituent enhances the rate of the reaction. So you have the alkoxide here, okay, that again will produce the carbanion, and a ketone is formed, and this carbanion is being protonated to get an alkane. So the rate depends again on the alkoxide and nothing else. Alright, now halogenation of ketones. This is either acid or base catalyzed halogenations. Even carbonyl compounds, both aldehydes and ketones, undergo this halogenation. You can see here, similar to the tautomerization which we have seen earlier, carbanion is formed over here. The base abstract the alpha proton, and we get a carbanion. And then the halogenation occurs. Alright, this the arrow mark must be full arrow here. The carbanion takes up a halogen from the halide ion or Br plus ion from the halogen molecule, and you get halogenated aldehyde. So alpha halogenation is happening here. Alright, and now if this is a symmetrical ketone, so no problem, but if it is an unsymmetrical ketone, the preferred site of abstraction of the proton is usually the most substituted carbon atom. So if you have a CH, if this group is highly substituted, then the proton attached in this group will be removed easily. So you can say that, see here, the order of preference for halogenation is more substituted alkyne moiety. So here, see here, this CH3 is being replaced by Cr2H. So here, what will happen? This proton will be removed. So more the substituted alkyl group on the ketone, it will be removed easily. The proton on it will be removed easily, and halogenation happens over here. Alpha halogenation. Now this is the same case in haloform reactions. That is, this particular proton is being replaced by I plus, and you see once this I plus is formed, the reaction, iodine is introduced over here, the reaction continues. Alright, until you get until all the proton has been removed and replaced by halogen. That is, complete halogenation of the ketone is happening. So once a particular site is being attacked by a halogen, then the complete halogenation of that site occurs. Then only it will move on to the next alkyl group. Okay, and finally you get here a haloform. Okay, you're getting an iodoform here. If you're using a bromine over here, bromine as a halogen, then you get bromoform. Alright, so that is the haloform reaction, which is very common, which is a reaction which we use to detect the presence of COCH3. You'll be familiar with this. So the electron withdrawing inductive effect exerted by the iodine or the halogen makes this alpha carbon more and more acidic. Alpha hydrogen more and more acidic. And that's why this is getting halogenated again and again. Complete halogenation of this position occurs. Alright, and the second halogenation will be faster than the first halogenation, because earlier for the first halogenation there was only the carbonyl group which is increasing the acidity of this proton. But in the second halogenation, this iodine group also increases the acidity of this proton. And when you come to the third halogenation, it will be still more acidic. So third halogenation would be faster. Okay, that's the case in the haloform reaction or halogenation of ketones. So haloform reaction also follows the SE1 mechanism. Now ketoenol tautomerism, we have discussed it earlier. Again, I'm just mentioning it here. The base catalyzed tautomerism is following SE1 mechanism. Usually the enol form, keto form is more stable, thermodynamically more stable than the enol form. And the enolization, the mechanism of this enolization is the base attracts the alpha proton, and you get a carbanion over here, and then enolate ion is formed, and then this oxygen abstracts a proton from the solvent, and enol is formed. We had discussed this earlier in the earlier slide when we were discussing about the evidence. So base catalyzed enolization is or ketoenol tautomerization is following SE1 mechanism. Nitrosation is another example wherein the acidic proton is replaced by nitrous group. Okay, so if you have an active methylene group like this here in this compound, this active methylene group, because it is being sandwiched between COCF3 highly electron withdrawing groups, so this becomes highly acidic and it can be easily nitrosated. Okay, so here NO plus is the electrophile or carrier of NO plus will be the attacking species. So this is the mechanism. You have the keto compound. Okay, and it is the enol form of it, and you have the nitro group, NO plus group here. It is attacking here, so you get the enol form is first formed C nitroso compound. Now the C nitroso compound is not very stable. It will abstract. It will a proton will be removed from here, and it forms keto form. Okay, and then you get a nitroso compound here, this nitroso compound and the oxime, they remain in equilibrium. Okay, nitroso and oximes are can be easily reduced to primary amines. So this particular reaction is used for preparation of amino acid. Alright, nitroso compound tautomerizes to the corresponding oxime. So this also follows SE1 mechanism. Another one is Helvolar-Zielinski reaction, the famous HVZ reaction, wherein bromination of acid carboxylic acid is possible. Alpha bromination of carboxylic acid is possible. Okay, that happens in the presence of phosphorus as catalyst. And remember, usually we cannot substitute the alpha position of the carboxylic group under basic condition, because instead of the alpha hydrogen, the base will remove this proton. So usually it's not possible. So HVZ reaction, Helvolar-Zielinski reaction, gives us a possibility of halogenating the alpha position of carboxylic group in basic condition. Okay, so you treat it with bromine in presence of PBr3, then you get alpha halogenated or alpha brominated carboxylic acid. Alright, now the mechanism here again, you have the carboxylic acid, the carboxylic acid, the OH is removed and the Br is replaced, so you get nucleophilic acyl substitution here. Br minus is getting attached over here, and then this undergoes ketoenol tautomerization. Okay, and then here in this step bromination happens. See here, this bromination follows SE1 mechanism. The second bromination follows SE1 mechanism. And then the carboxylic acid, another molecule of carboxylic acid, will donate a proton over here, and you get alpha brominated carboxylic acid. This Br is removed, and this Br, now you get the acyl substituted bromine compound. This is similar to this compound, and then this continues, the cycle continues. Okay, so that is the story of alpha bromination of carboxylic acid, which otherwise is not possible under basic condition. So this acyl intermediate undergo bromide exchange over here. So you can see here bromide exchange, and then the carboxylic acid here also bromide exchange happens, and the catalytic cycle continues until all the carboxylic acid is halogenated. Okay, so this, and one more thing, this reaction is not applicable for iodine or fluorine. It's applicable only for bromine. Another important reaction is Stockinemine reaction, which follows SE1 mechanism. Now, it is a method wherein the ketones are alkylated or acylated through enamine intermediates. The steps involved in this reaction are, there are two steps. Basically, you can divide the reaction into two steps. First, the enamine is formed. That is when the aldehyde or the ketone reacts with the secondary amine, we get enamine. See here, you can see. And this enamine will be attacked by the electrophile on the alpha carbon of the enamine to give the substituted ketone. Okay. Now this, first the attack will be on electrophile attacks on the alpha carbon, followed by hydrolysis. So a new group is introduced onto the alpha carbon of the ketone. So if this electrophile is an acyl group or an alkyl group, you get alkylated ketone or acylated ketone. This acylation or alkylation is happening on the alpha carbon. That's important, which otherwise is not possible. Alright, so this is a very important reaction, Stockinemine reaction, wherein also again SC1 mechanism is followed. Now, the reaction can be looked upon in more in detail. How is the electrophilic attack happening? See here, the double bond of the enamine goes and attack. The electrophile comes over here, and the iminium ion is formed. And then another example, similar example for this is here. You can see this ketone is being attached to the alpha carbon of the cyclohexanone. Okay, so here what's happening? This double bond, the pi bond, attacks this double bonded carbon over here. Okay, so this pi bond attacks over here, not on the carbonyl carbon. Remember, not on the carbonyl carbon, but over here on this double bonded carbon, and you get the alpha substituted compound. Another example, here you are getting 1,5-dicarbonyl product. Another example wherein you get 1,3-dicarbonyl product is same reaction, but you are using acyl chloride. Okay, when you use acyl chloride, you get 1,3-dicarbonyl product. So what's happening here? This will go and attack on the carbonyl carbon. Okay, so you get 1,3-dicarbonyl product. So to get 1,5-dicarbonyl product, you use to get 1,5 and 1,3-dicarbonyl product, you use different reagents or different substituent or different attacking moieties, and accordingly you get different products. So this is for enamine reaction, Stockinemine reaction. Now coming to, when this electrophilic substitution sometimes is accompanied by double bond shift, as in the case of allyl system. We have seen this for nucleophilic substitution also. So when the allylic systems are the substrates, then there will be rearrangement, there will be double bond shift. So here you can see the base abstracts the proton from here, you get allyl carbanion, which will resonate or which will be stabilized by the shift of the double bond, and the carbanion becomes a primary carbanion. And accordingly, you will be getting the product, a secondary product or a primary product, depending upon the population of the resonating structure. Okay, so usually this is more stable because this is a primary carbanion, and you get this product. Okay, there is an double bond shift over here. Now another example is another reaction which we need to understand is Diazo D-dihydro bisubstitution. Compounds containing active methylene group as malonic ester can be converted to diazo compound when you treat it with tosyl azide in the presence of a base. Okay, so you have a active methylene group. This is malonic ester, for example. Okay, at the active methylene group, you are treating it with tosyl azide in the presence of a base. You get azo compound. Okay, you get diazo compound. So this Z and Z dash, the Z prime can be COR electron withdrawing groups. Again, remember. Then only this will become highly acidic, this proton. The methylene proton must be highly acidic, so the groups adjacent to it must be electron withdrawing. Now, this is called the diazo transfer reaction. You can use this reaction for cyclopentadiene also. Now, how is this happening? The base abstracts the methylene proton, and you get a negative charge carbanion over here, and you have the tosyl azide here. The tosyl azide will be, the nitrogen on the tosyl azide will be having a positive charge, and then there will be attack. So you can see here the nitrogen will be attacked, and then you get the diazo compound. Alright, so that is the mechanism for this one. This negatively charged nitrogen will take up this proton again. This is again acidic proton. Okay, and so you can see here the nitrogen abstracting the proton, and this proton, the electron pair goes to the CN bond, and then one of the electron pair on the NN will go to the other nitrogen, and then tosyl group will be, TSNH will be removed. Alright, now another reaction is aliphatic diazonium coupling reaction. Again, there must be the active methylene group, okay, and we get diazonium salts. CH bond, acidic CH bond is replaced. Similar reaction as what we had earlier discussed. If that was a azide over there, we are introducing this diazonium group into the compound. Okay, see here active methylene group, the hydrogen is replaced and we get the diazonium salt is introduced. Okay, so here also again Z can be COET, Z prime can be any electron withdrawing groups, Z and Z prime. The aliphatic azo compounds where the carbon containing the azo group is attached to hydrogen are unstable and tautomerises to the hydrazone. So that's why you have the hydrazone here. So to summarize whatever we have discussed till now, electrophilic substitutions involve the replacement of the group or hydrogen on the substrate by an electrophile. And when we talk about the SE1 mechanism, it is a unimolecular reaction following first order kinetics with respect to substrate, and it proceeds via two steps, that is redetermining proton abstraction step, formation of carbanion, and then formation of the product by the attack of the electrophile. Then the product is which we get is usually a racemic mixture, and since the carbanions are stabilized by electron withdrawing substituent, SE1 reaction are favored by substrate which has got electron withdrawing groups attached to it, and not favored by substrates in which electron donating groups are attached. And polar solvent favors SE1 mechanism because of better solvation of the carbanions, and solvent also decides the stereochemistry of the mechanism. So this is a summary of what we have discussed till now in this video. Hope it's clear to you. You can refer more books, texts, and you will get more information regarding this. Thank you.